Okay, you are now live. And welcome everybody to a Hyperledger meetup. I'd like to introduce the speakers today who will be speaking about Fabric Private Chaincode. So with that, take it away, please.
All right, thank you, David, for hosting us, actually. All right, so I think you see also that screen. Let me try to make it a little bit smaller. So can someone say that you still see my screen?
Yes.
Awesome. Okay. All right. Let's talk about Fabric Private Chaincode. So I'm super happy that we have the chance today to share this exciting project with you. So this is the project is called Fabric Private Chaincode. We are a Hyperledger project. I mean, for providing a new feature for Fabric with the subtitle confidentiality. Confidential chaincode execution for Hyperledger Fabric using Intel SGX. So today we are three speakers. So it's me, Marcus. I'm with IBM Research in Zurich. Then we have Maria with Home Lending Pal. And then we have also Bruno from Intel Labs. And I suggest that we should start with the motivating. So why does this project exist? Okay. Can I move that somewhere else? Maybe here, maybe even smaller. Great. Okay, so I hope that the audience is familiar with blockchain technology, and that even we have people here on the call who are familiar with Hyperledger Fabric. I think that's also the chance to check if this can be an interactive session. So I would suggest if someone is familiar with Hyperledger Fabric, please hit a plus in the chat channel and see if we have some people here actively listening. Awesome, I see pluses. That's amazing. All right. Okay, so even more pluses. Awesome. So I guess, I mean, since you know Hyperledger Fabric, I don't know, maybe you have already thought about privacy-sensitive use cases on Hyperledger Fabric. So what do I mean with sensitive use cases? So there, I mean, we know that blockchain technology is nice for very different applications, in particular for the verifiability aspect, which is provided by blockchain. However, there are use cases which come with certain security requirements, in particular privacy requirements. Let's take a few examples here. What I mean with that. Think about a sealed auction. There we understand that in the sealed auction or a secret auction, the bid secrecy should be maintained during the auction, and in the end, an auctioneer reveals the winner of an auction. Very similar e-voting, right? So we understand that in the e-voting scheme or in a general voting scheme, we submit our ballot, and this ballot should maintain the secrecy, right? And nobody should ever learn what was my particular vote. But also healthcare use cases where, for instance, genomic data analytics is happening. There, we also have a quite good understanding that those genomic data is very sensitive data because it allows to identify humans, right? It helps to identify people. And in a supply chain use case where multiple organizations, they would like to exchange assets for some value, for some money, right? But certain contracts should not be revealed. In particular, people are not really interested in, let's say, revealing the price they paid for a certain asset to a competitor, for instance, right? So luckily, Fabric already comes with a bunch of privacy mechanisms built in. So for instance, we can have channels Some of you may already know the concept of a channel, so we can actually split the blockchain in multiple blockchains and only let people participate in the channel who need to participate. For instance, in the supply chain, we could say, okay, only the two organizations which are interact with a contract, they are on that particular channel. That excludes automatically competitors from that channel and from the details of that contract. A second mechanism is private data collections, for instance. I think there was talk about that here on this meetup, I think in November. So there we learned a little bit more what that means. However, to recap, the basic idea is that we use the ledger, the blockchain, only to store hashes of the data we are exchanging or using in our smart contract, and the real data goes between the organizations through the data collections in some way of offline communication, direct communication. And then the third thing is transient fields, which allows us to add data to a transaction without adding it to the transaction. That means we can submit data to the smart contract, to the chain code, without this data ending up in the transaction itself, which is then later committed to the blockchain or stored on the blockchain. However, all these mechanisms, they have a problem. And this is the data visibility at the endorsing peers and the respective organizations. So what do I mean with that? So think about that. In Hyperledger Fabric, there are endorsing peers executing or running a smart contract, computing a result, then sending it back to the clients, and then a transaction is generated and submitted to the network. However, these endorsing peers, they execute the smart contract, and in order to execute, they need all the data. If we now take our voting as an example back here, even if the ballots are in some way encrypted, they need to be decrypted at some point by the smart contract processing them. And then there's some computation who actually won the election. That means that the endorsing peer, from a security perspective, has access to the clear data. If we now imagine that the government would run such an endorsing peer, then we could say, well, maybe this is not a good idea, right? Depending on if you trust your government or not. But I mean, this is just an example, okay? And so, and in order to overcome now this problem of data visibility, we introduce what we call Fabric Private Chaincode, which is a framework to build, deploy, and run private chaincodes on Hyperledger Fabric. So Fabric Private Chaincode accommodates blockchain use cases with strong privacy requirements, for instance, those examples I just gave. And it does it by executing the chaincode or the smart contract by using hardware-based trusted execution technology like Intel SGX. And by using that trusted execution technology, we basically get 3 security properties for our application which uses Fabric Private Chaincode. The first one is confidential compute, which means that all the transaction and the ledger contains only encrypted data. The second is verifiable operations, where transactions can be or are verified through a mechanism called attestation, which is something provided by the trusted execution environment. I will come to that also in a second. And the third property is data misuse prevention, because with this technology, it allows us to bind the data we are using in our transaction to the intended chain code. Okay. Let me quickly talk about Intel SGX. So the idea of Intel SGX is that you take your little piece of code you would like to protect in a certain way and put it in a container or in Intel SGX speak often called Enclave. which helps you to reduce the trusted compute base, the TBC. That means that if my application runs in such an enclave, then we only need to trust, of course, the trusted execution technology, but only the actual application running inside such an enclave. When we think about the traditional way, how the trust model in Fabric or any other application works is that we have our application. In Fabric, this means our peer, or Fabric peer, which executes a chaincode. And this relies on the operating system. It relies on the trust of the operating system. And the operating system relies on the trust on the hypervisor, on the hypervisor on the hardware, and so on. So if we now, do a computation in that model, we just need to trust the entire box, the entire machine, that the execution of the chaincode is correct and that nobody steals my data. With introducing into SGX, this picture changes a little bit, what you can see here on the right side. And it changes in a way that we take now our chaincode, our smart contract, put it in a so-called enclave, which is protected by the hardware itself. This changes our security model in a way that we do not need to trust the peer anymore, but we only rely on the hardware, or the trust in the hardware, and the application itself. And by using this technology now, we get essentially, let's say, 3 basic security properties. The first one is confidentiality. That means that only the enclave sees the data which it processes. So that means that the peer, for instance, cannot look inside the memory of the enclave, for instance, and extract certain secrets. The second is integrity, where the hardware ensures that the intended application, in our case, the chaincode, is executed as intended. And the third property is verifiability, which links to the property I've mentioned before, the hardware-based attestation, which allows a third party to ask the application running inside the enclave, hey, application, are you running inside a trusted execution technology, and what are you exactly? And that process of attestation will then produce a proof that it executes a certain application or chaincode inside a proper hardware-based trusted execution environment, like an enclave. So with this understanding now, or this brief understanding what Intel SGX is, I think we can look in how we're using this actually. I think you get the rough idea now. We're running our chaincode, our smart contract inside SGX. For more details on SGX, I would definitely recommend to look on the documentation on the Intel website if you want to learn more about that.
Marcus, there is a related question in the chat. Indirajit is asking, Intel stops its SGX with its processors, right? Would it affect this function? So,
Okay, so I can answer that. Or Bruno, do you want to answer this?
I guess I can answer the first part. Maybe you can follow up. So Indirajit, I guess you're referring to the unavailability of SGX on some client processors. Well, that's the case, but SGX is still available on server processors, particularly on Isolate, for example, where you can have a larger enclave size, so you get more performance. So SGX is available. Marcus?
Yes. I can try to answer the second part of the question. Would this affect this function? And yes. So if the processor does not is SGX capable, then we cannot use it in that case, right? That's definitely a risk. However, I think it's very interesting because there are, other TEE, trusted execution environment vendors, which provide similar technology. Right now, we Fabric Private Chaincode focuses on Intel SGX because it fits clearly in our security model, because we are interested in protecting a chaincode application. Other TE technologies like AMD SEV, they aim to protect entire virtual machines, which are much bigger than just a chaincode. This is just maybe to give you an intuition why we are using Intel SGX here. But in general, I would say our architecture, which we have not talked about yet, is also applicable to other TE technologies other than Intel SGX. But with this, let's have a look at the architecture. So this gives you, again, just a rough overview or brief overview on what Fabric Private Chaincode looks like. So what you can see here on this graphic is, the basic components of a standard Fabric network. We have a bunch of peers, we have an ordering service, and we have a client or client applications, which all together interact and allows us to run applications on top of the blockchain. From the previous slide, we already got the idea, okay, that now the chaincode runs inside an enclave, which isolated from the endorsing peer. And through that hardware mechanism, all the memory content of that chaincode or of that application is actually protected from the peer. So this is the first, let's call it the big change. The second big change is that we are injecting a little bit of additional logic in the deployment phase of a chaincode, where initially a consortium which runs or wants to use a chaincode together, they agree on something called a chaincode definition. And in a chaincode definition, we now include what we call MR enclave, which is a unique identifier of the application or the chaincode running inside the enclave. And this vehicle we are using to enforce that only the expected chaincode protected by Intel SGX is used during the lifetime of the smart contract or the chaincode.
Marcus, we have two questions. One
Awesome.
is Luciano, who's asking, what would be the advantage of isolating chaincode from the peer?
So I hope I was already answering that question indirectly with my motivation slide. So the idea is that, in a or the general thing in a blockchain system is that a smart contract is executed by multiple participants. So if I'm working for IBM, if IBM runs a peer, I can trust that organization to do a proper execution. However, we know that in Fabric, we can specify an endorsement policy which says, okay, this chaincode needs to be executed at multiple organizations. But what if I do not trust one of those other organizations entirely? So I would reveal my sensitive data to that organization. Let me bring back that example of a voting. If the government runs a voting system, it runs a peer, right? I would send my encrypted ballot to that peer of the government, and the government needs to decrypt the peer in some way. Okay, let's not talk about, I don't know, multi-party computation, homomorphic encryption, things like that. That's orthogonal to that. But so the key point is that you maybe there are also situations where you trust the organization, but you maybe do not trust the host where this peer is actually hosted. Maybe that peer is, I don't know, hosted on a malicious cloud provider. So there are definitely some cases where you are not fully trusting a peer. I hope that answers that question a little bit.
And then,
sorry.
yes.
Only one more question to complement the other one. So this enclave from Intel is something centralized where the chaincode lives?
Well, it's not centralized in that sense. So every peer would run an enclave, and every enclave, I mean, an enclave belongs to the peer in the end of the day. But I mean, as I explained, we have a different trust relationship here. But I mean, the thing is that we should still have the opportunity to send our transaction to multiple peers, multiple enclaves to do that. I don't know if you're already familiar with Fabric Private Chaincode and then saw something different. So there is, so we have some implementation limitations at the moment that our current prototype only supports a single enclave per chaincode. But I mean, this is an implementation issue, not a conceptual issue.
I see.
Any other related questions to that? I think it's very nice when people are asking the questions instead of typing them.
Adam made a question and says, how do you make sure that the code is run in SGX hardware and not in some kind of emulation layer?
Yes, so for that, there exists this mechanism called attestation, what I was also mentioning before, which let the hardware produce a cryptographic proof which you can verify later. And that actually plays together with the identifier of the actual chaincode as defined in the chaincode definition using that hash of the application, the MR enclave. And with this cryptographic proof you received from the chaincode, you can verify that and ensure that this was not generated by an emulator layer, for instance. There are, of course, SGX simulation modes, which cannot provide such a proof, but then there exists a fake proof, which you can clearly see that, hey, yeah, this is a fake proof. This does not run in a protected environment. It's not secure, but maybe it's still useful for developing purpose. All right. Any other questions?
No, not for now, at least on the chat.
All right, so let me now finish this slide here and then I will give to Bruno. So two more things. So as I've already said, so now we have protected or isolated the chaincode from the peer. And in order now to communicate, we also need to establish, let's say I call it a secure channel between the actual application and the chaincode through the peer. That means that Fabric Private Chaincode gives you a mechanism in form of the FPC client SDK, which you can use in your application, which is responsible for exactly doing that. So it's responsible for encrypting and authenticating all the transaction inputs in a way that only the chaincode inside the enclave can decrypt and then use that data. And the same actually happens for all the data which is stored on the ledger or in particular on the word state. You know that a chaincode can access the word state by performing get state and put state operations. And there the FPC chaincode makes sure that this data, which is stored outside the enclave on the word state, is encrypted in a way that only the chaincode inside the enclave can later decrypt and access the data and clear again. All right, and I hope now we have an understanding, so what we can do with Fabric Private Chaincode. And with this, I would like to give to Bruno to talk about a particular use case in the healthcare area. And let's see how this is useful to use. All right, so Bruno, do you want to take over the share screen?
Yes. Okay. Hopefully you can see my screen.
So we still see PowerPoint, not the full screen version at
Right.
this moment.
There we go. Okay, so let me discuss this use case on healthcare, and particularly on clinical trials that we developed with our partners at SoftThread, a startup that deals with works in healthcare. So, brief background on clinical trials. Well, probably you are a little familiar with this. So these are this is clinical research that is performed to assess the safety and efficacy of drugs and treatments for people. And this use case was interesting for us because there are several individuals and parties that participate in these clinical trials, and in the end there are lots of regulations and data to be protected, and of course you need some means to automate all the procedures and making sure that security is preserved. Now let me quickly go through some peculiar aspects of these clinical trials. So as I said, there are multiple parties, and to make a simplified picture, you can see that there are at least 4. You have an institutional review board that takes into consideration and approves proposals for clinical trials for investigators. You have subjects that provide the data that has to be eventually analyzed. The investigators conduct the trial, and maybe some experimenters will take care of actually analyzing the data in order to get to a result. Now, there could also be multiple institutions, but just to keep things simple, right now, let's just deal with a single one, which is already complicated enough. Now, since you have to deal with patient data, then there are some regulatory compliance to deal with. Like, for example, you always have to make sure that you maintain the safety of the participants, or in the US, for example, you have these HIPAA rules or regulations, which mandate that the data is treated according to some standards, like it always has to be protected. There must be access control. You have to preserve the integrity, and always encrypted. It must be always encrypted when you store it somewhere. So there are several objectives that must be met in order to comply with this clinical trial, with the regulations. And one thing that is not shown in the figure is the auditing capability. So there is another party, usually public department, that takes care of auditing these clinical trials to check post facto whether something has happened, and then take some countermeasures. Maybe something that was happened, like in data treatments, and in that case, some fines will be issued. So what are the challenges in these clinical trials? Well, the big question here is how to automate and secure them. Now, let me point out that we're not talking about automating and securing the physical collection of data from patients or blood samples or anything like that. Here we're talking about digital data and how to automate and secure its analysis. Now, of course, if you are able to automate these procedures, well, you reduce time, you save some, and you save some cost. Now, for data management and regulatory compliance, things get more complicated, simply because you have multiple parties to deal with, and you have to understand where do you place trust, whether you place that on the individual or on the institution, and how can you better reduce the trust boundaries in order to improve security in these cases. Just one second. Okay. So the usual, so the first question that comes up is, how do we solve this problem? And usually the first answer is, well, let's use a blockchain. And this is what our partners started to do. Blockchain in this case means that if before forms and sensitive data were collected through paper forms, for example, well, now they can be easily collected and distributed by using a blockchain such as Hyperledger Fabric. Now, although this works and brings some benefits because you are really automating these procedures, well, things have not really changed from a privacy or confidentiality perspective, simply because before you had individuals trading paper forms, and now you have still individual trading PDF forms, for example. So you still trust the individuals, and the approach that is being followed from a security perspective is a trust and verify. It means that, okay, I'll give you my data and I trust you not to do anything unintended. And I trust that there will be some auditors in the background that will control what you do, that will check what you do. And with the digital data is basically the same thing, but and still you're relying on the auditors. And perhaps things are even a bit worse because by using a blockchain, you're actually distributing this data to a multitude of parties, simply because the blockchain is shared by default, although it can be permissioned in the case of Hyperledger Fabric. So how do we solve this problem in with FPC? Well, the idea in FPC is that you can reduce the privileges that you delegate to the parties. Now, here I have a complicated pictures of what happens logically, but hopefully I can help you make sense of that. So initially we had direct interactions between these parties, like the subject and the institution to provide consent for data processing and also the data itself, or you have the institution delegating the conduct of the trial to the investigator. So the idea in FPC is to logically centralize all the steps and the verification of the steps inside an enclave. But again, I said logically centralized because we are building FPC on Hyperledger Fabric, so it's in practice it is decentralized. So this enclave would essentially contain all the implementations to gather sensitive data from the subject, as well as any approvals from related parties, like the IRB for the approval of the clinical trial, or the investigator to approve experiments that the experimenters are intended to run. And only when all the regulations are met and the appropriate checks also are have been analyzed and controlled by the enclave, only in that case the enclave will take care of transferring the sensitive data from the experiment approval chain code to another experiment, always inside an enclave, in order to protect confidentiality. So by doing this, you reduce reliance on individual parties and actually increase trust on automated and verifiable third-party agent, which is implemented inside the enclave, which is supposed to implement all the regulations and checks that will allow you to eventually increase trust and security on data management. Okay, so this is a picture of the demo that we actually built with our partners. Again, I understand it's a bit intricate and big, but it is a big and complicated use case, indeed. All these components and whatever we built, you can find that on our repository on GitHub. So I will just walk you through these components to give you a better idea of what's going on, and then I will show you a video for how it works in practice. So again, you can see the different parties that I showed you before. So the ARB that approves the clinical trial, and the approval of the clinical trial and the consent part from the user. These are have been implemented by our partners, and they are based on plain Hyperledger Fabric. The big challenges came when we had to deal with secrets and manage confidential information, and in that case, we didn't want, of course, to release those to all the peers on the Fabric network, and for that reason, we wanted to rely on FPC, and so on hardware-based confidential executions or chain codes for Fabric. So what happens here is that the subject will register some data with the experiment approval chain code, and it's a registration with a promise in this case. And the promise is that is something like, promise me that you will not release the data to parties that have not been previously approved or experiments that have not previously approved. So again, that enclave is supposed to implement all the policy and regulations that have to be enforced. The investigator will take care of approving any experiment that the experimenters want to run. So in this case, the subject does not have any a priori knowledge of what will be the data analytics in the experiments, and that's reasonable because there may be different ones that can come up. And once all the approvals and the registration is in process, then the experimental approval chain code inside the enclave can determine whether the experimental data, so the subject data, can be provisioned to the external enclave or not. And if so, it will be provided to another enclave at the experimenter side, and the data analysis will happen, and it will just release the final result to the experimenter. So let's go through the video here. So we implemented the different parties in this case, particularly the data provider, which is the subject, an experimenter which will run the analysis, and the principal investigator who has to approve the software before being used. Here we have some patient forms. I will show you the what they contain. That will be sensitive data. We have a diagnose function, which is the data analysis that the experimenter wants to run, and a console on the side that just to keep track of what's going to happen. So this is the patient form. Is a standard PDF with sensitive information like the name of the patient, birth date, and some questions that the user has to answer, like the temperature, whether nausea occurred, and so on. And the point of this PDF form is that eventually the experimenter has to understand whether the subject has a high probability of having this nephritis of renal pelvis origin. So this data will have to be analyzed. Okay, so let's play the part of the data provider or the subject. So the subject uploads the data to our blockchain, select some options. During the upload phase, what happens is that the data is encrypted first, and the secret encryption key is registered on the FPC chaincode, while the encrypted data is instead uploaded to an external database. This is really an optimization, simply because the blockchain is an expensive database, and so you don't really want to use that to upload arbitrarily large data. Okay, once this is performed, let's play the part of the experimenter. The experimenter decides that he wants to run an ML machine learning inference model over the sensitive data. And to do so, he decides to use this diagnose Python function, which will use the patient data to make the inference. Now, the important part here is these data items. These data items are the variables in the code that will contain the sensitive patient data. But of course, the patient data still has not been disclosed to the experimenter or to this function for the analysis. Okay, so the experimenter submits a description of this experiment together with the code to the investigators for approval. The investigators are notified that there is an experiment pending approval. Here, 3 of them are alerted of the new experiment, but according to the policy that we implemented, a single approval is sufficient for the experiment to be approved. So the investigator has access to all the information about the experiment, the description, and particularly the code that is able to review before making a determination. In this case, everything is fine. So the investigator goes ahead, approves the experiment. Now the FPC chaincode considers that as completely approved, and the experimenter is ready to launch an instance of this experiment. So what are you seeing here is an instance of the other enclave, the second enclave, the one that contains the experimentation service. And this enclave is the one that contains the experiment code, and it's the only one that is able to interact and authenticate itself with the FPC chaincode for the sake of making sure that the experiment was approved, and so that this enclave is eligible to receive the sensitive patient data. So there is a public key for authentication and also for establishing a secure channel. The experimenter runs the experiment, receives the patient data, the enclave grabs that from the external database, and eventually it is able to get the final result, which is 19%, and this is the probability that that particular subject has of having these nephritis of renal pelvis origin. And again, this is the only information that is eventually released to the experimenter. This is because it's how we implemented that. And so the experimenter did not have access to any patient data. So we were able to preserve the confidentiality from when the data was initially provided to the experimental approval chaincode, to the FPC chaincode, up to when it was eventually analyzed without ever releasing that. Okay, so this concludes the experiment, the use case.
We have 2 questions.
Sure.
One is from Neo, who says, in this use case, does the subject need to hold a private key for transaction signature? If yes, may I know where is the PK held? And does the Intel SGX have access to subject private key? May I know if it performs inside SGX?
Okay, so yes to both. Yes to both. And the reason is simple. The subject has to, of course, authenticate itself in these procedures. In the end, it's a client contacting an FPC chain code, and since this is based on Fabric, well, we have a Fabric client and a Fabric chain code in the background. So for the sake of authentication, yes, and those keys are held locally at the subject side, and they are, yes, they're used to essentially trigger transactions on FPC. I would also add that these public keys should also be registered with the chain codes, simply because the FPC chain code has to authenticate or verify that the subject indeed is a subject enrolled with the institution for that clinical trial. Now, the second part of the question is, does the enclave use some public and private key pairs? And the answer is yes, and of course yes, because it has to perform some digital signature of what it's computing, and also it has to authenticate itself with other parties, because parties such as the subject has to make sure that it is talking to a legitimate enclave. So these enclaves, these keys are generated by the enclave at startup time, and they are attested through the hardware-based attestation mechanism that Marcus quickly introduced before. So in the end, the chain of trust that you will eventually verify in order to establish trust in those keys is that you will verify the hardware. The hardware will tell you that it is running a certain piece of software, which is this experiment approval chain code. And this piece of software will include those public keys inside this attestation. So essentially, you verify the whole chain, you establish trust in those keys, and eventually you can use even the private key inside the enclave to sign any statement. Other questions?
No, the other question, Marcus answered it on the chat.
Okay, so again, this demo is available on our repository. Talk to us if you need additional information about this or about how to run FPC or the demo itself. And I will stop sharing, and Maria can take over. Stop share.
So while we're switching here the gears, I mean, so our repository is on GitHub. It's called Fabric Private Chaincode. We also show the link later here in our slides, but I can just answer this question while we are changing things. Fabric Private Chaincode. Just Google it. You will find it first hit.
So just to do a bit of a recap, okay? This is the architecture and what are the components that we have to develop? So there are two components, the FPC chain code and the application that is accessing and calling that chain code, right? So how do you develop both of those? The first one is the chain code. How do I develop the chain code? So the chain code, you have to develop it on C++. This is because since we are running in a trusted execution environment that is using SGX, this is a requirement of SGX to develop in C++. Now, we have provided a shim to be able to handle a lot of the logic that is required to do the encryption, decryption, processing, and all of that. We are actually, that shim is on top of the current Fabric chaincode functionality. So this is not completely different from what you can get with the Fabric chaincode. The only difference is that here, when you, for example, here you call the get state or the put state, you will not have to encrypt the parameters before, because that will be done when the invocation is made. Okay, so you only have to import our shim. As with any chain code, you have to develop the invoke, and this is where you would program the chain code logic. Now, if we move on to the client side, we need Fabric provides a Fabric client SDK in Go. So as with the chain code, we develop on top of that SDK. And since the Fabric client SDK is in Go, the FPC client SDK can also be in Go. This SDK manages not only the interaction that we have, like here, that we have a submit transaction and an evaluate transaction, but also the life cycle. So all of the functionality to be able to implement, deploy a chain code into an environment. Okay, here we can see that we get a contract, we submit the contract. Here we can see the values. Again, that is because the shim is the one that is doing all the transformation. And here we have an evaluate transaction. Okay. And how so that's the theory of how everything is done. Now I want to get my hands dirty. Can I do that? Well, this is the link to our GitHub repository, where you're going to be able to find all the things that you need. And if you don't, you can ask us, or you can post it, and we'll try to help you out, right? The important thing is also that you're going to say, and one of the first questions was, Intel is not continuing with SGX. And Bruno said, no, it's not doing it with the client processors. So if I want to develop, I don't have a big Isolate server where I can have the SGX. How can I do that? We provide Dockerized development environments that can simulate that SGX. So if you've got the hardware, well, better for you. We still do provide a Dockerized development environment, so you can run everything in there and make it more simple for you. And if you don't, doesn't matter. You're going to be able to develop the same way, because you're going to be using SGX simulation. Now, in our repository, we have different samples. Okay, the simplest sample is the Hello World tutorial that will help you not only develop the chain code, but also develop the Fabric client to be able to access and execute that chain code. Okay, and one of the questions that was asked on YouTube Live was, I want to add it to my network. How can I do that? One of our samples is, hey, remember the Fabric sample of how to create a test network? Well, we show you how to add Fabric Private Chaincode to that sample. Okay, so that way you learn how to do it with a test network, you create your own network, we'll follow the same rules and just add the bit that we have added so that you can do that. And it's not only with the test network, but also with Kubernetes. And Bruno just presented the IRB demo. And something that I would like to add to that is he mentioned that it is in our repository, but also that there we are using the Fabric Smart client. What does this mean? He showed all of the different participants. So that network is not a simple network. And if I'm a developer and I have to set up all of those peers to run on my laptop, well, it's going to take me a long time, okay, because it's not already set up. I have to do it. So we piggyback on top of Fabric Smart Client that provides programmatic logic to be able to define that network and get it created. And that simplifies the development process. It also has the ability, we've integrated it. So from Fabric Smart Client, you can also call our utilities, our chain codes. And that way it makes it much simpler to be able to develop a solution to whatever your problem is. And I've tried to, we've got 2 minutes left for questions. I wanted to take you guys to the GitHub repository, but I think it's going to be much more useful if we open this up for any questions. If you're on the Zoom call, you can unmute your microphone and ask a question. Or if there's already a question in the chat, we can answer it.
So there's a question on the chat. Hubert is asking, is it possible to interact with other blockchain? Say I want to build a smart contract on, say, Ethereum to give some token to those giving away their data on Fabric blockchain. How difficult would it be to implement? I think this is a good question. I also think this is a little bit beyond Fabric Private Chaincode. Well, I mean, my answer is, I don't know, actually. But yeah, I mean, you can definitely build a Fabric Private Chaincode, which can, let's say, process details of inputs data you're also presenting to an Ethereum smart contract, I guess. But so we do not provide any functionality or any layer which makes, let's say, our technology stack compatible with, for instance, Ethereum. I hope this answers the question at least a bit. Any other questions? Just feel free to unmute yourself and just jump in here.
Okay, I guess it's 10 and PST at least.
Yes,
I guess we can wrap up.
Just one last question. Marcus, I don't know if you want to answer it. Alexander was asking about the chain code lifecycle.
Yes, absolutely. So, I mean, with Fabric Private Chaincode, we are, let's say, exactly following the same chain code lifecycle. I mean, you have to package it, you have to install it, I mean, deploying it, you have to approve it. I mean, all the organizations, they have to submit an approved by my org transaction. And then at some point you have to do, I think it's called a commit chain code definition transaction. The only thing what changes here is that as part of the chain code definition, we add the unique identifier of our chain code inside the chain code definition. And with a unique identifier, I'm referring to that hash of the, let's say, the hash of the compiled chain code, the expected chain code. So we add this to the chain code definition. So this is one piece how it changes. Then we have a component which we call the Enclave registry, which is implemented as a chain code. We have not talked about that yet today because this is nothing we're exposing to the users of FPC. So our client SDK and our entire framework tries to hide that component. However, it is crucial for security because when it is used when a chain code actually is started. There is this process of or there is one additional call we add to the lifecycle, which is called register enclave, which an admin of an organization using our SDK performs at a certain peer, which tells the peer, hey, please start an instance of that FPC chain code. That FPC instance then does what Bruno explained a little bit. It produces some crypto keys. It produces a remote attestation, which proves that it runs a certain chain code and it's protected by the hardware. Then this attestation is sent to our Enclave registry component, which looks at the proof and checks that this proof contains exactly the same hash which was defined previously in the chaincode definition. And only if that matches, then we actually allow the enclave to be registered and to go live in the system. That's one thing we have not talked about today. One other minor thing is, I mean, this goes really into technical deploying details for Fabric Private Chaincode, is that we are relying on the external service functionality of a peer in order to spawn a chaincode. As you know from Go chaincode or JavaScript chaincode, there you normally, when you install it on a peer, you tell the peer, hey, here's the code, please compile it, package it as a Docker container, and then there is a Docker container running at the peer. Our entire build framework gives you the tools in order to create that Docker container for you. Then this will be shipped to the peer. And by using the external service or the chaincode as a service mechanism, the peer is able to communicate with this Docker container where now our FPC chaincode is running. Those are, let's say, in just 2 minutes, how the lifecycle changes. But we really try to keep as close as possible to the normal Fabric lifecycle. Maria told you about the Fabric samples test network. If you go to that tutorial on our repository, you will see those individual steps very well explained in the README. You can follow them, and I think then it should, everything should be clear how this is different from a normal chaincode lifecycle. All right, I think we're over time. Are there other questions?
There's one last question. Is it possible to use FPC to privately store input data on the ledger to be processed later? Similar to voting, the votes will probably be calculated at some moment in the future.
Absolutely. So this is actually the use case for Fabric Private Chaincode. The idea is that we send our data in a way that it is only visible to the actual FPC chaincode. The FPC chaincode can then store that data on the ledger in an encrypted form. And at some point when you want to process this data, you can trigger the chaincode and tell, hey, now it's the time, please do something with the data. The chaincode gets the data, decrypts it, processes it, and without revealing it to the endorsing peer. That's actually the use case of FPC, right?
And last, just to finish, I want to invite anyone who liked the idea and wants to help out. We meet on Tuesdays. You can check the time on the calendar, on the Hyperledger calendar of when our meetings are. And we are open to anyone to new contributors. So,
all right,
David.
Yeah, thank you. Thank you,
David.
Thank you for everyone for joining. And yeah, hopefully we will talk again soon.
All right. Thank you, guys. Have a good evening.
Thank you, everyone.
Or
Have a good day.
Thank you.
Bye, everyone.
Bye-bye.
Bye.